Today, we're going to break down one of the most fundamental, most important concepts in all of probability theory, the Bernoulli process. Okay, so here's our game plan. We're going to start with this super intuitive idea, literally just flipping a coin. From there, we'll build up the formal math behind it. Then, we'll get into its really surprising properties. And finally, we'll unpack why this simple little process is actually considered a universal model for randomness itself. So let's kick things off with an image we all know, something that really forms the foundation of how we even think about chance. Well, you might be wondering, what's the most basic, bare-bones way we can model randomness as it unfolds over time? It turns out the answer is something we've all known since we were kids: flipping a coin. Not just once, but over and over and over again. So what are we really talking about? At its heart, a Bernoulli process is just that, a sequence of repeated coin flips. Now, the coin could be unfair, maybe it lands on heads 60% of the time, but, and this is key, that unfairness has to be consistent. In more formal terms, it's the simplest non-trivial stochastic process you can have, where each step has only two possible outcomes. You can call them heads and tails, or as we usually do in math, success and failure, 1 and 0. All right, so we've got the analogy down. Now let's get a bit more formal and actually build the mathematical object that represents this. Everything starts with one single event. We call this a Bernoulli trial. Think of it as just one toss of the coin. It's a single experiment with only two outcomes, and it's all governed by a single number, the parameter p, which is simply the probability of getting a success. And the Bernoulli process itself? Well, that's just what you get when you string a whole bunch of these trials together in a sequence. And the two magic words you need to remember here are independent and identically distributed, or as you'll always hear it, IID. So let's really hammer this home, because it's absolutely crucial. Independent means the coin has no memory. Getting heads on the 10th flip tells you absolutely nothing about what's going to happen on the 11th. And identically distributed means that probability of success, P, never changes. It's the same for the first flip, the 100th flip, and the 1,000,000th flip. That's the consistent unfairness we mentioned earlier. Okay, so now that we have this process defined, we can start asking some really cool questions about it, like, how do we count the outcomes? And what's so amazing here is that a bunch of really famous, really important probability distributions just pop right out of this simple process. If you ask, hey, how many successes will I get in, say, n trials? Boom, that's the binomial distribution. If you ask, how long do I have to wait for the very first success? That's the geometric distribution. And if you generalize that and ask, how long until I get r successes? Well, that gives you the negative binomial. They're all just different ways of looking at the same underlying process. Right, so that very first question, the how many heads will I get in 100 flips, is answered perfectly by the binomial distribution. Its existence is a direct, beautiful consequence of those IID properties we just talked about. But here's where things get really wild. We can look at this whole thing from a completely different angle, from the world of dynamical systems. Okay, I want you to picture that infinite sequence of coin flips just stretching out in front of you. Now, the Bernoulli shift is a transformation, an operator, that does something really simple. It just chops off the very first outcome and scoots the entire rest of the line one step to the left. You just forget the past and move on. And here is the magic trick. Because every single flip is independent and has the exact same probability, the new sequence you're left with is statistically identical to the one you started with. It's still a Bernoulli process with the same P. This incredible property makes the Bernoulli shift a textbook example of a measure-preserving ergodic system. That's a fancy way of saying it's a system whose statistical properties don't change over time, and that if you wait long enough, will eventually explore all of its possible configurations. All right, so what happens when we let this process run for a really long time? This is where some of the biggest, most famous theorems in all of probability theory come into play. This one is probably the most intuitive. The law of large numbers is the formal guarantee, the mathematical proof, that if you flip a fair coin enough times, the proportion of heads you see is going to get closer and closer and closer to 50%. It's the reason casinos always win in the long run. You can almost see it happening. After just 10 flips, who knows, the proportion might be way off. But after 100, it starts getting closer. 1,000, even closer. And as you head towards an infinite number of trials, that observed average just locks on to the true underlying probability, P. But it gets even better. Not only does the average zero in on the right number, But the way it bounces around that average, the errors, the natural fluctuations, they follow a beautiful, predictable pattern. And you've definitely seen it before. It's the classic bell curve, the normal distribution. Okay, so we've gone from simple coin flips all the way to bell curves, but so what? Why does this one seemingly basic model get so much attention in advanced mathematics?
Well, its fingerprints are absolutely everywhere. In information theory, it's used to define the fundamental limit of data compression, something called entropy. In computer science, it's the engine behind random walks and how we generate random bits. And of course, in statistics, it's the very first model you reach for when you want to test if a coin is fair.
This idea of it being universal isn't just some poetic description. It was actually formalized by a mathematician named Donald Ornstein in the 1970s. His work, the Ornstein Isomorphism Theorem, is a massive result in ergodic theory. It basically says that a whole bunch of other random processes that look way more complicated on the surface are, deep down, mathematically indistinguishable from a simple Bernoulli process. It's like discovering that all these different, complex engines are secretly running on the same simple two-stroke motor. It makes the Bernoulli process the ultimate benchmark for a huge class of randomness.
And this leaves us with a final, pretty powerful thought. The humble coin flip, it isn't just a game of chance. It's a window into the deep mathematical structure of randomness itself. It's a simple key that unlocks some of the most profound ideas in modern probability and ergodic theory.